Hey there, I'd like to introduce a new feature of CME2 version 8.0, and it's motor characterization and tuning. If you have the ratings label on the side of the motor, you probably have sufficient data to do the characterizing and tuning. You still have to figure out how to hook up the feedback and the motor wires. So, it's probably a good idea to get some motor specifications from the motor manufacturer to make sure everything is set up properly. But sometimes I understand it's difficult to get information from a motor manufacturer about their motor. I understand that. So let's take a look at the new CME2 8.0 motor screen. And you can see there's no longer a feedback tab because we enter that in the basic setup. But the default configuration are just some parameters there to hold a position place. If I do not have the motor specification, then I would use the ratings data. And the ratings label for this one says 3,000 RPM. That's the nominal speed. And it looks like I have an intensity current of 4.51 amps, and I have a rated torque of 0.4 Newton meters. There's a watts there too, but all that information is unnecessary. I can hit characterize and tune, and it'll use this data to help determine the motor specifications, just from the measuring stuff, as much as it can. So let's give it a whirl. So the first thing that the procedure does is, it says disabled by hardware. So that we didn't get very far this time. So we need to enable the drive. So we got the stow in. So we have to, the low enables the drive. Okay, so we're software disabled because it's EtherCAT, but we're hardware enabled and stow enabled, so we should be good to go. Let's give it a second try here. So the motor's inductance and resistance will help determine the tuning values. I'll hit start, but if we don't have the motor's inductance and resistance, then the auto tuning will tune the current loop, and we don't have to worry about the inductance and resistance. Although I like to measure the motor's resistance with an ohm meter, measure the resistance across a pair of wires, and if we don't know the inductance, you just put that same value in for inductance. It's a ballpark figure, but knowing the winding resistance is always good, especially while the motor still works. Because when the motor stops working, maybe it overheated and the resistance is no longer the original value. So I like to know what that is so that I can check things out when things go wrong. So use an ohm meter to measure the winding resistance. Okay, so it determined the current loop bandwidth here, got some values for CP and PI, told us the current loop bandwidth is 900 hertz. That's sufficient. I like to say 1.2 kilohertz plus or minus 200 hertz, but it's not breaking neck spindle speed, so I think this should be fine for a 4-pole motor. So I'm going to jog the motor forward as the positive direction. You can see that the motor shaft is rotating clockwise, and next. All right, make sure it's going to spin, so make sure nothing's in the way. So this is open loop microstepping. It's trying to determine the phase. It's kind of hard to do that test connected to a load, so my recommendation is disconnect the load. Although it will apply sufficient current, open loop, still a load may hinder some progress there. So now it's just confirming that the motor went in a positive direction. I saw it go clockwise. I'm going to say yes. I want that to be the forward direction. So it's checking out the counts per rev. I said 2048, which is 8192 counts per rev. I said it was a 4-pole motor. It can determine that itself, but you got to start somewhere, so counts per rev is a good place to start. And we can take a look at the motor specification later. Mavelar Infinor does a good job providing the motor specs. Now, this is the acceleration test to determine the inertia. Applies a step current. Now here's the velocity step test to set tuning values for CP and CI. So step response tuning characteristics. So it gives us a VP of 109 and a velocity integral of 24, and it says we have a bandwidth of 70 hertz. We're going to tune and characterize. Oh, that's it. We're done. Okay, so now the tuning, the auto tuning's done, and gains must be saved into Flash. So don't forget to save the Flash. You can do that right now. All your hard work goes to waste if you don't save the Flash. But if we go back and look at the motor information, I know this is an FP00348 motor. Yeah, it's 4-pole, but you can see the data that it calculated based on its findings. It gave us a 0.1 kilogram centimeters squared for inertia. That looks pretty close to the spec data. 0.8 Newton meters, that's what we entered. 0.4 continuous. Well, we entered 0.4. It took twice that for continuous, so this motor probably has a lot more than 0.8 for peak, but it's a nice safe value that is not from the spec. I got a 0.08 Newton meters per amp based on the torque and torque constant we gave it, and given the volts per radians per second is an equivalency. It can also calculate the back EMF. So let's take a look at the motor specification here for this motor. We can see it's a 48 volt winding and it's a 0334. It's got a 48 volt rated speed at 6,000 according to the spec, although it does says 3,000 for the nominal speed. I know this motor though, it can go like 30,000 RPM, so don't be afraid to spin it fast. It's a slotless motor with a captured magnet cage around the magnets. So yeah, I got 2.2 ohms and 0.7 millihenry here. I got a 0.01 kilogram centimeter squared. Kilogram meter squared times 10 to the minus 3 is the same as kilogram centimeter squared. So let's take a look at the data here. So we know it's a 2.2 ohms and a 0.7 millihenry, and well, it says the inertia is 0.01, but our software came out with a 0.1. There could be some frictional differences, I don't know. Peak torque, 2.4, so we can go ahead and use the peak torque there, 2.4. So all these are good motor datas, and we can save that to the Flash. So these values that we have here now are the auto-tuned values, and there's the speed limit, slightly over the rated speed. So let's take a look and see how this stacks up if we were to look at the tuning ourselves. So just a quick go through on the auto setup checkbox, apply to the current. So good current loop tuning. Let's do the velocity. A little bang, 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 back and forth. Reading trace data here. Give it a minute. Yeah, that looks pretty good. A little more integral maybe for steady state, but I like that. Sometimes I have a little less integral myself. And 8192 for 1 rev. Yeah, that took 1 rev, so the encoder count's correct, so the pole count's good too. And, well, that's not bad. We'll give it a little bit more integral here and see what that looks like. No, maybe a little bit too much. Try 40. I'm not gonna say the software did a bad job tuning it. think he did a pretty good job, but we can always go in and tweak things a little bit with manual tuning. It used a filter pole of 200 hertz, two-pole filter. When I do my velocity tuning, I like to bring it in for not much load, maybe a one-pole 200 hertz with little load, and have a large inertia, maybe a 50 hertz single pole with a little higher gain. But all in all, I'd say we did a pretty good job here. Save that to Flash, and we're done characterizing the motor based on just a very little bit of data. Thanks for watching.